Thank you for attending this presentation. Today, I will give you an overview of the project I'm conducting on my PhD. This presentation is titled Unveiling Changing Eruptive Style After Sector Collapses in Basaltic Arc Stratovolcanoes, with a few examples from the Eastern Pacific. So today I will talk about what the sector collapses produce, and then I will go to the basaltic volcanism in arc settings, describing basaltic volcanoes and edifice instability, with some definitions regarding two sector collapses and processes occurring after the sector collapses, like unloading the plumbing systems, and the examples from the Eastern Pacific, with some future scope and perspectives. So in this case, when we talk about sector collapses, we immediately think about the 1980 eruption of Mount St. Helens in Washington. So when a volcanic edifice is destroyed by this kind of processes, the debris avalanche and the debris in general produces a huge damage and massive changes in the landscape around the volcano, changing not only the hydrology and geomorphology and killing the biota temporarily, and also producing some impact, sometimes very, very important in communities living around volcanoes. At least 3,000 people have died in the last 400 years as consequence of this kind of direct processes. But there is another process more important in this case than the debris avalanche itself, and is related to the tsunamis generated by sector collapses. For instance, we can think about the 2018 eruption of an Krakatau that was responsible for killing about 400 people in Indonesia after the sector collapse of this volcanic edifice. So when we think about basaltic volcanism, we think about Mesozoic ridges and hotspot volcanism with these huge amounts of basalts. But in the subduction zones in arc settings, it is not very common to see purely basaltic volcanoes or dominantly basaltic volcanoes. Because it is difficult for basaltic magma to ascend through the crust to the surface of the crust, because they are overall compressive regions, compressive settings. So extension is not absent, but is uncommon. I thought transtension and transpression is more common in those settings, and they may favor the ascent of basaltic melts, which are generated by slab dehydration, and commonly they are stored by basaltic underplating below the crust. So basaltic volcanoes have different forms, different shapes. For instance, basaltic spatter cones, cinder cones, volcanic fissures, some ferromagmatic geomorphologies such as mahars or tuff rings. And we can also find shield volcanoes in arc settings, and more commonly these kind of stratovolcanoes. In the back arc setting, we have also volcanic fields constituted by basalt, and also we have some basaltic floodings. But in general, the most important thing regarding to basaltic stratovolcanoes is that they are made up of a huge number of different layers of interbedded lavas and pyroclastes, and also volcaniclastic deposits. So Those complex structures are able to become unstable if internal processes such as magma ascent or hydrothermal fluid circulation can produce some sort of deformation, seismicity, or thermal changes in this, or strength changes by thermal action in the rocks, but also external properties such as climate, glacial retreat, or debasement properties can change the condition of stability of the volcano, producing landslides. And in general, sector collapses are volcanic landslides affecting the flanks of the volcanoes, and they are catastrophic and usually fast-driven in terms of geologic processes. But they encompass a large quantity of different features or different ways in which volcanoes collapse. So they encompass from small summit or valley field collapse, like in the Fuego eruption in 2018 in Guatemala, to huge sector collapses like that one of Krakatau volcano in Indonesia. And they can maybe trigger different magmatic processes. So here is a picture of how sector collapses and their debris avalanche deposits develop, and the mobility and volume of them. So basaltic volcanoes cover a wide spectrum of these kind of landslides. And after the depressurization produced by the lack of mass in the volcano, the magma can suffer oversaturation in volatile, or may trigger crystallization, undercooling, and the increased melt viscosity. So it will depend on the storage depths of the reservoirs, the shape of the reservoirs, and the size, of course, of the collapse, the loss of lithostatic pressure given by the collapse. So this lot of changes produced by the sector collapse in terms of a stress regime can alter the system and cause both larger or smaller eruptions, or even the cessation of an ongoing eruption. And of course, the magma pathways can be affected, and deeper intrusions of renewed magma can start after the sector collapse, producing mixing or mingling of magma and rapid regeneration at the end of the cone. So I will describe a few aspects of these examples. Pacaya is in Guatemala, Planchón Petoroa and Antuco are in the southern Andes, in the southern volcanic zone. In the case of Planchón Petoroa, is in the border between Chile and Argentina, and Antuco is in Chile. So in terms of those examples, Planchón Petoroa is the oldest and the biggest. It occurred about 11 kiloyears ago, and the volume was about 10 cubic kilometers, producing a huge deposit that is distributed up to 95 kilometers from the source. In the case of Antuco, it is younger and not as big as the Planchón Petoroa example. It occurred about 4,000 years ago, and it involved 5 cubic kilometers, and the new cone is almost regenerated in the exact same place of the sector collapse. And Pacaya experienced a sector collapse 1,000 years ago, and it involved 0.6 cubic kilometers. So in terms of stratigraphy, what we can see in the field is that the debris avalanche deposit in Planchón Petoroa is covered by a series of alluvium and fluvial deposits, but in some places, in some sections, there is a lava flow directly above the debris avalanche deposit, and it was the first activity or renewed activity after the sector collapse. In terms of Antuco, the debris avalanche deposit, which is not very clear here, but trust me, is there, is covered immediately by pyroclastic density currents, so an explosive eruption. And after that, you have two lava flows which are covering the pyroclastic density currents. So there was an explosive eruption immediately after the sector collapse, and two effusive eruptions after the explosive phase. And in this case, those lava flows are the longest ever seen in Antuco volcano. And in terms of Pacaya, even when the debris avalanche deposit is directly covered by scoria fall deposit, in some sections you can see clearly how the blast deposit related to the directed explosion during the sector collapse is in between two tephra layers, PT5A and PT5B, which represent an ongoing eruption during the sector collapse, which was interrupted and enhanced by the sector collapse. So three different styles of reaction after the sector collapse. So I want to know what caused the sector collapse in first instance, which were the pre and seen eruptive conditions of their eruptive activity following the sector collapse, the immediate post-collapse activity, what controls the effusive explosive behavior of each case study. You have to remember that we are talking about basaltic volcanism, which is not very oftenly explosive, and how to extrapolate this model to other arc stratovolcanoes. So some of the results that I have is, in this case, the mapping of the debris avalanche deposits with some remote sensing on the hummocks, which gives some clues on the mobility and the physical properties of the flow. This is for Peteroa, and I have some preliminary constraints on the storage system for Planchon Peteroa, for Antuco and Pacaya, which give some ideas of the depth of the magmatic or the shallow reservoir. In the case of Planchon Peteroa, it was very shallow, and that can explain somehow the triggering mechanism for generating this huge debris avalanche deposit when the volcano was so active and so big. So my project is advancing right now in the petrography, glass and crystal chemistry, crystal size distribution, and in general, textural and compositional analysis of the scoria samples related to the magmatic stages just after the sector collapse, trying to understand the conditions of storage and the changes induced by this loss of pressure in the magmatic system. I will still work on the debris avalanche deposit, describing its stratigraphy and phases and componentry in order to understand the potential causes or triggering mechanisms of the landslides. And a very important part of this work is related to numerical modeling of the reservoirs and how it reacts to this loss of lithostatic pressure given by the sector collapse. So this is intended to generate a coupled geological and numerical model on the effects of sector collapses in basaltic magmatic systems. So this is the reference slide, and thank you so much for attending this presentation. I hope you have some questions and I can give you some answers. Thank you so much.